So, good morning, everyone. I think we should get started. So, I'm pleased to introduce my colleague, Lucas Ambrosio, as the first speaker today. So, Lucas earned his PhD from IMPA in 2014 under Fernando Codá Marques, and he subsequently held postdoctoral positions at Imperial College, Warwick, and at the Institute for Advanced Studies in Princeton. And he has been back here at IMPA as a faculty member since 2020. So he will tell us about Zoll-like metrics in minimal submanifold theory.
Thank you very much. Good morning, everyone. Right, now, okay. So thank you, Henrique, for the kind introduction. Welcome, everyone. So I should say that 10 years ago, I was a PhD student, maybe sitting over there, I don't know, and attending IMPA's 60th birthday conference. So I'm very happy to be, well, part of this. Okay, so I started to think about Zoll-like metrics in minimal submanifold theory because I sort of convinced myself that I should understand this kind of geometry in order to understand the equality cases in certain geometric inequalities that I was thinking about. But I looked at the literature and I was quite surprised to find very little about this, to the point that there is not even a proper name for these objects. And I mean, when I define the object, I think you will agree with me that they are very natural and also very interesting to anyone thinking that likes geometry. Okay. Okay, but since those geometric inequalities may be a bit far-fetched, if you never thought about them, I decided to motivate the problem by talking about two very old problems about geodesics. One problem that was formulated by Eugenio Beltrami in the 1800s, and the other that David Hilbert proposed to his PhD student, Otto Zoll. Okay, so it's a problem about geodesics, so let us talk a bit about them. So they are curves in a manifold. I will always be thinking about a Riemannian manifold. And they are curves that belong to two different realms, so dynamical systems and geometry. From the from the dynamical point of view, I can define geodesics as the trajectories of particles moving with no acceleration. So if you remember Newton's laws of movement, then you can easily conclude that the geodesics of the plane or the Euclidean space are just the straight lines, right? And you can also see that the law that governs the movement of such particle is given by a second-order homogeneous ODE. And this is important because it tells us that for any given point on the manifold and for any given tangent vector at that point, you can know for sure that there exists one and only one geodesic that passes through that point with that given velocity. Okay? Okay, so from the geometric point of view, on the other hand, I can define geodesics as those curves that are locally the shortest path between 2 points in it. So what do I mean by this? So if I take 2 points on my geodesic, and if they are sufficiently close to each other, then I know for sure that this piece of geodesic in between them is exactly the curve that has the smallest length among all curves that go joining those 2 points. Okay, so this curve here has more length. Okay? And this is basically everything that we need to know. So now let me formulate the problem of Beltrami. Actually, a question, maybe. which was a question about maps in the geographical sense of the word. So he was thinking about a surface in R3, something like this, and he wanted to find certain special representations of small neighborhoods of this surface. So he wanted to find certain charts representing this neighborhood as a region of the plane. And he wants to impose a certain condition on phi. And what is this condition? So the question was, can I find a chart that makes the geodesics on the surface correspond to straight lines? In other words, if I see a geodesic going to this region, I want to find a chart such that this piece of geodesic is represented by some segment like this, or this one by another segment like this. Okay? And I need to do one remark because there is a subtlety here, a subtlety that Beltrame, of course, was aware of, is that I don't want this map to preserve the length of the curves. Right? So if I measure the length of this curve on the surface, I don't want to impose that this length is equal to the size of this segment. And this is because the very famous theorem by Gauss, the egression theorem, which tells us that in this situation, I would have a map preserving length, so this map would be an isometry. And in particular, I would be able to conclude that this region is flat, has zero Gaussian curvature. Okay? So I would be talking about a very, very special case, and Beltrame really want to find this chart maybe for different surfaces. Okay, so the remark is that we allow length distortions. Okay, so when Beltrame started to think about this problem, he knew just one example of such map, the central projections. So let me draw here the Euclidean sphere. So this is S2, the Euclidean sphere. And it's very easy to compute what are the geodesics of the Euclidean sphere. So this was very well known, geodesics. So they are the great circles. And the great circles are what you see when you intersect your sphere with a plane that goes through the center of the sphere, right? So something like this curve here. Okay? Okay, so what's the central projection? So you have to imagine this sphere sitting on top of a plane, tangentially at the south pole, say. And then you need to shoot the rays from the center of the sphere towards the plane. Okay, so it will hit the sphere at some point, and then the image of the map will be the point it hits the plane, right? And from the definition, it's not very difficult to conclude that the image of great circles will be straight lines, right? So the great circle determined by this plane here is going to be, the image of this circle is going to be the intersection of this plane with this base horizontal plane here. Okay? So this was the key example, the only example actually that Beltrame knew. Okay, so now I can state what he proved. Beltrame in 1865, I think. So he proved the following. So if there is such chart, and this chart is not an isometry, let's rule out the trivial case, then maybe after composing your chart with a map of the Euclidean space that sends lines to lines, right? So maybe after composing the chart with an affine map, then the metric is determined. So he computed the coefficients of the metric, and the expression is something like this. So there are two parameters, two constants. And I will write down the formula. So it's something like this, r squared, a squared plus, so u, v are the coordinates on the plane. So u squared plus v squared, this multiplying a squared plus v squared du squared minus 2 u v du dv plus a squared plus u squared dv squared. Okay? And once he got this expression, he could use Gauss regression theorem to compute the curvature, the Gaussian curvature of this metric. And what was the result of the computation? Well, the Gaussian curvature is constant and equal to 1 over r squared. Okay, so constant. And right, so basically, his initial hope of finding, maybe for a general surface, a map like this that could be useful, maybe in practical sense. I mean, you could be, it would be easy to represent the geodesics on the surface, but well, he concluded that such map does not exist very often, right? So only when the surface itself has constant curvature. Okay. Now let me make maybe two historical remarks. So the first one is about a work that Beltrami wrote maybe 3 years later. The work that made him maybe famous. It's a work about hyperbolic geometry. So Beltrami, what he did this work actually, I was amazed to discover that what he did was he took a and r to be equal to the square root of -1. Okay, in that formula there. So he took a and r to be the unitary imaginary number. And well, he got then a geometry with constant negative curvature -1, but a geometry that was defined not for every u and v on the plane, but only, you see, you have a -1 here, so this will only make sense when this quotient is non-zero. So he got a geometry defined only on the unit disk. So took, and then on the disk, u squared plus v squared less than 1, this geometry given by this Riemannian metric with constants I, he showed that this is exactly a model of Lobachevsky geometry. So, okay. So this model, I mean, it's not the model that we are most used today. We are more used to the Poincaré model. But this model is also very interesting because of what is the special property of this model? Well, the geodesics are the straight lines. So the lines in this model of hyperbolic geometry are the chords. Right. According to this geometry, those lines have infinite length, as they should. And I mean, it's immediately obvious to see that this geometry does not satisfy the parallel postulate. Okay, so this is the first historical remark. And the second one, we need to go a bit further in time, to the beginning of the 1900s, when Hilbert proposed his famous list of problems. And the problem that I want to mention is the fourth problem. Does anyone remember by heart what is it about? So this problem is about straight lines as the shortest path between 2 points. So remember that at this time, 1901, right? So he was also thinking a lot about the foundations of geometry. And in his mind, this was a problem, a very abstract problem. So what he wanted to understand were the geometries on the plane or on the space, such that if I pick 3 different points, then they lie in a Euclidean line, if and only if they satisfy the equality case in the triangle inequality. Okay, so that was what he was thinking about. So this metric could be anything, not necessarily given by a Riemannian metric. And so this led to, several interesting works by people like Buzem and Pogorelov, which would take us too far away. So what I want to mention is that if we interpret this problem as, so if we interpret geometry as Riemannian geometry, then this problem was solved by Beltrami already. Okay, so in Riemannian geometry, there is nothing new. Aside the constant curvature geometries, constant. So Beltrami's theorem gives the 2-dimensional case, but actually he later generalized to all dimensions. Okay, so Beltrami did that, and at the same time, this guy called Scheffli also did it. Scheffli. Okay. Okay, so we arrived at Hilbert, so I can now state what was the question that he asked his student to work on. And remember that also in the beginning of the 1900s, as we all know here at IMPA, Poincaré was convincing everyone working on, with a dynamical system given by a ODE to look at the periodic orbits of such system. And the geometers, of course, knew an interesting example of dynamics such that all orbits are periodic. Right? So the remark is, if you think about the sphere, it has the properties that all of its geodesics are periodic embedded circles. And so Hilbert asked his student, Otto Zoll, are there other metrics with this property? And Otto Zoll, I think he surprised everyone in 1903 when he answered this question in the affirmative. And actually, he found spheres of revolutions in R3 with this property. Okay, so now I find it hard to believe, so I decided to show you the picture. So here you see, thank you. So here you see the Euclidean sphere, some geodesics, some great circles on it. And then you also see this surface of revolution here with some geodesics in it. And, well, given any point and give any direction, if you follow the geodesic, it will close itself with the same velocity eventually. Okay? Okay, so it was very amazing because the first time I gave a talk on this subject, it was a remote talk at ETH, and Mario Schultz, who is a postdoc at Münster, the next day he sent me this picture. And I asked him, oh, wow, how did you manage to produce those pictures? And he told me, I went to Zoll's paper. I could see there the ODE for the generating curve of this sphere of revolution. Then I plotted it, and then I solved the geodesic flow. And so I got those lines in there, okay? So it's an amazing picture. And this was the beginning of an entire field of investigation. So you probably know a book by Arthur Bess named Manifolds, all of whose geodesics are closed, right? So Zoll inaugurated the topic by constructing those examples. And I want to mention now, this is a theorem that will appear later, but let me mention it now. I think from 76, a theorem of Guillemin, that found, so he found examples near the canonical metric that are not necessarily of revolution. So there are really, really many, many examples of such objects. Okay. Very well. I think now it's time to introduce to define what is a Zoll-like manifold in minimal submanifold series. So what we want to do is to go to higher dimensions, but not. We don't want to talk about curves in a higher dimensional manifold. We want to talk about submanifolds in these higher dimensional ambient manifold, right? So we need to go from curves. Let me write it here. So we need to go from curves to submanifolds. So we need to find the right analogus of geodesics, right? Now, the dynamical interpretation of geodesics is very hard to generalize. But the geometric interpretation is quite obvious, right? So because since geodesics are those critical points of the length, so they locally minimize length, the notion that I want to consider is the notion of minimal submanifolds, which are those submanifolds that are critical points of area. Okay? So if you pick a sufficiently small region on your surface, the condition that imposes is that this piece of surface has the least length among all pieces of surface with the same boundary. Okay, so this looks a bit like a difficult condition to check, but it's actually a local condition, so you just need to compute the mean curvature vector of this surface and check if it's identically 0 or not. Okay? So this is the equation, if you want, that defines a minimal surface. Right, so now what do we want to do? We want an analogous notion of a Zoll metric on S2. And since we uncouple the dynamics with the geometry, we need to be a bit careful and maybe distinguish between the topology and the geometry of this situation. So I will first define the topology. So I want to consider, to simplify things, only the case of the sphere. So I will take Sn, the unit sphere in Rn plus 1. And what I want to do is to study a family of embedded n-1 dimensional spheres in Sn. Okay, a family that satisfies further properties. So sigma will be family of embedded Sn-1s in Sn. Okay? So I will say that this is a Zoll family when the following conditions are met. So let me write down the conditions first, then I discuss 3 conditions, A, B, C. So the first condition is that I want the parametrizing set of the family to be RPN. So the parameter space should be RPN, the set of lines through the origin in Rn plus 1. So the second condition is that if I pick a point on the sphere and a codimension 1 tangent plane at that point, so a point in the Grassmannian, then I should be able to find a unique element of the family. So there is a unique sigma such that the corresponding surface, so it contains the given point P, and its tangent space at the point P is exactly the given hyperplane pi. And the last condition is I just want these maps defined by A and B to be smooth. So I don't know, sigma, sigma, sigma defined by A and P pi associated to this sigma defined by B. I want those two maps to be smooth. Okay? Okay, so this is just to keep us inside the smooth world. But let me talk about those two definitions. So this one has an obvious analogous for the case of geodesics, right? So after all, a geodesics is uniquely determined if I know a point where it passes and I know its velocity. So I want to distinguish a family which is uniquely determined by this data point, tangent hyperplane. And the other condition is inspired by the case, the model case that we have, which is the case of the standard canonical metric and the family of equators, right? Because the main example here, the model situation, is the family sigma sigma consisting of the intersection of Sn with the orthogonal complement of the line. So these are the equators of Sn, right? So I give a line, then I look at the orthogonal complement. This is the surface that I'm defining. Okay? So this family here satisfies A, B, and C. Now, for the canonical metric, the equators are minimal hypersurfaces. Then the question is, the new problem is, can I find more examples? In other words, are there Riemannian n-dimensional spheres such that admitting that contain a Zoll family of embedded minimum Sn minus 1s. Right, so we are asking the same question that Hilbert asked, right? But in a more complicated setup. Okay, so now I can tell you about what I did regarding this problem. This became a part of a joint project with André Neves of the University of Chicago and Fernando Kodá from Princeton. So this became a joint project with Fernando and André. And the project was, well, let's try to find examples, okay? And then there were two approaches that we that looked promising for us. Two approaches. So the first one would be to try, well, since we know one solution of our problem, right? So the pair canonical metric and equators, maybe, like Guillemin, we could try to find a new solution of our problem nearby, right? So the first approach was to perturb a known solution, canonical metric equator, family of equators, into new example where the metric is maybe close to the canonical metric, and this family is some sort of perturbation of the family of equators. And the second approach was very much inspired by Beltrame's theorem. So the second approach would be to try to solve the inverse problem. In other words, I give you a Zoll family, the family of equators, and I try to compute the metrics that make all equators simultaneous minimal hypersurface. Inverse problem. So solving the inverse problem, in other words, SNG, find G such that all equators are minimal. In the same way that Beltrami kind of asked all straight lines to be geodesics. Okay, so let me state the results that we obtain. So let's see. How are we with time? Okay. Are we with time for both? So let me talk a bit about the first problem. Okay, so about one. And this is a theorem that works for all dimensions. Okay, so theorem, Marcus Neves. Right, so let's take a symmetric two tensor on the n-dimensional sphere. So think of this as a tangent direction in the space of metrics on S2. And let's assume this guy is such that if I restrict it to every equator, every standard equator, and if I compute the trace of this tensor with respect to the canonical metric, and if I compute the average of that, this should give me 0 for every equator. Okay, so equator orthogonal to sigmas. Okay, so this is the condition. I will talk more about the meaning of this later. But then, okay, so what's the conclusion? So if you give me this tensor, then I can find a smooth one-parameter family of Riemannian metrics GT in some small interval, a family that starts at the canonical metric, so G0 is the canonical metric, and the initial speed of this variation is the given tensor H. Okay, with them, such that Sn with this Riemannian metric GT admits contains a Zoll family of minimal Sn minus 1s. Okay, so this guy contains some Zoll family of minimal embedded Sn minus 1s. For any? For any t, yes. At 0, it's just a family of equators. And then for a small t, it's a family that's made by perturbed equations, equators. So small perturbation of these equators, graphical perturbation of these equators. Okay, so let me go through a few remarks. So the first remark is the following. So what's the meaning of this condition star, right? So the first thing is that we can completely characterize those tensors, okay? So any symmetric two tensor can be decomposed into 3 pieces. One that's tangent to conformal deformations, so it's a function times the canonical metric. One that's tangent to those deformations coming from one-parameter families of diffeomorphisms. So this is a Lie derivative of the canonical metric. And then the directions that are transversal to that. So these are given by some tensor H bar which satisfies this condition. It's a TT tensor. It doesn't matter much what it is, but think of this as the directions that are transversal to conformal directions. Okay, so what's the condition? What's the meaning? So what does star tells us about this decomposition? It only tells us that the only restriction really is that this f must be an odd function. Odd with respect to the antipodal map. So f of minus x equals to minus f of x. And this is the only restriction. Right, so the other thing to say is that this condition star is actually the necessary condition for such a deformation to exist. Right, so what we are proving here is that there are no further obstructions aside the first order obstruction in order for you to get this deformation. Okay, so necessary condition, star is the necessary condition. And this, the fact that this is the necessary condition, in the two-dimensional case, was an old result by Paul Funk in 1916, I think. So he already knew that in the classical case of Zoll matrix on the two sphere, this oddness here was the necessary condition. Okay? And so it was a bit surprised, right? Because in two dimensions, because of the uniformization theorem, you know there is only one conformal structure aside modulo diffeomorphisms. So in two dimensions, the decomposition doesn't see, there is no transversal direction, right? But in high dimensions, you have. And it was a bit surprising, well, to see that there are no restrictions at all. Okay? This H doesn't need to be odd. I mean, any transversal tensor works. Okay, so the second remark is that, yes, so if I restrict my initial speed to be conformal, so if I take an initial h, which is just a function times the canonical metric, then actually we have a version of this theorem that tells us that we can take this family inside the conformal class of the canonical metric. So we may take GT to be of the form e to rho t, some positive function, times the canonical metric, where, well, at 0, rho is 0, and the initial speed of this is the given function, odd function f. Okay, so we can make the deformation inside the conformal class of the canonical metric. And this generalized that theorem of Guillemin result. So the theorem of Guillemin that I mentioned earlier. So, so this generalizes exactly what Guillemin proved in the n equals 2 case. Okay? And actually, although similar, our argument is different from Guillemin. So somehow we are giving a new proof of his theorem. Because Guillemin could rely on dynamic consistence, right? So he was working in dimension 2. So he used this structure of the geodesic flow to formulate his problem and solve it. But while here, we only use the variational geometrical characterization of our objects. Okay, so it's a new proof. And finally, the last remark is that for generic choices, it's interesting to observe that the corresponding family given by the theorem is such that the isometry group of this matrix is trivial. Okay? So, in other words, those objects, I mean, this condition of being Zoll doesn't impose no, well, it does impose no restriction at all on the symmetry of your surface, right? So they can be as asymmetric as they can and still contain a Zoll family of minimal hypersurface. The Now, the H lies in an infinite dimensional space of all.
It's asking whether your star condition is codimensional.
No, it's infinite codimension, right? So the only restriction is being odd. So you have all the even functions which was on the complement, which are okay. Okay, so and actually this, this kind of answered the question by Yao, because Yao, once you have a one-parameter family of isometries and a minimal surface, you move by the isometries, then you get a one-parameter family of minimal hypersurfaces. And Yao asked if this would be possible with no symmetries at all, right? So the answer is here, but actually there are most examples are of this kind. Okay. Right, so let me see. Good of time. So maybe let me say 2 words about the proof. So the idea.
But we also have a formula for the general case.
To compute the isometry group?
No, for
No.
the family of metrics.
No formula at all. No formula at all. It's an application of an inverse function theorem, right? So the idea of the proof, so let me just say with words, so what the idea is. So the heuristic is that we want to treat the problem as an analytic problem on a pair of variables. So we have this equation, everyone is minimal, but this equation depends on the metric and on this Zoll family. So we want to solve this equation here, right? And the idea would be, well, heuristic, right? So if we could prove that 0 is a regular value of this nonlinear map, then the inverse image would be a nice submanifold. And then we could integrate our tangent vectors at the standard pair into new solutions. So the aim was, well, let's try to prove this inverse image is a nice submanifold. Okay, so you need to linearize the operator. When you linearize on this side, this gets you something that's easy to understand. So you fix the metric, change the surfaces. So this gives you Jacobi fields, so the solutions of a certain second order elliptic PDE. You have Fredholm alternative. You know when you can invert. You know how to compute the kernel. So this part of the linearization is fine. The problem is the linearization in this first variable. And this is where this condition appears, right? Because basically, not to understand the generalization of this first variable, what you need to understand is this map that picks a symmetric 2 tensor on the sphere and sends it to a function on RPN, which compute those averages on each equator. Okay, so the kernel elements should be the ones that are in the tangent space of my submanifold. So these are these. The problem is to prove that the derivative is surjective, right? So then things become complicated. The analysis of this operator, which is an integral operator, is much more delicate than the analysis of Fredholm operators. Okay. So in other words, I had to study a lot about I don't know, integral operators and. It was a bit annoying because they don't usually think about those problems on manifolds. They use Fourier transforms and, well, this is all nice, but on a manifold, it's not quite straightforward how to do it. Anyway, okay, so this is the idea. So now let me say a few words about 2, which was that inverse problem, okay? Now, remember the central projection. Right? So if I have a map such that all equators are minimal, I can push it forward to the plane by a central projection and get a metric on the plane such that the straight lines are minimal. So in 2 dimensions, we can rely on Beltrami theorem. Beltrami theorem tells us nothing new, right? So the problem is solved by Beltrami. And how about n greater or equal than 3? Now, following this observation about the central projection, I think the natural question that you could ask is, well, maybe let's do the stereographic projection and look at metrics on Rn plus 1, or Rn, such that all hyperplanes are minimal. Right? That looks like I mean, people should know about this, right? But to my surprise, only in 1996, I think, or 97, Theodore Hangan solved the question. So he studied metrics on Rn plus 1 with minimal hyperplanes. And basically, he gave a recipe. So he can associate every such metric to an element of a space that it's completely understood. Okay? Now, adapting his method and being a bit more systematic about this kind of studies, so we could prove the following statement. So it's also with Marques and Neves. And the theorem is the following. So there is GL n plus 1 equivariant bijection between the two sets. So let me write them here. So G is the set of metrics on Sn with minimal equators. And the other side of the dictionary is the set of algebraic curvature tensors in Rn plus 1 with positive sectional curvature. Okay, so those are the tensors that have the same algebraic symmetries as the curvature tensor of a Riemannian manifold. And so there is this bijection between this set and this set. And the good thing is that we know that this guy here, this set here, is an open cone of a vector space of dimension n plus 1 square, n plus 2 divided by 12, I think. So if this gives you 20 when n equals 3, this should be right. Anyway, so it's an open cone in a finite dimensional space. So the moduli space of this solution of our problem is completely determined. Right? It's quite surprising, right? So because this is obviously something that attracts a lot of attention of geometers because, well, there are open problems about metrics with positive sectional curvature. When, for each manifold, do they exist, and so on. Okay, so this is what we can say about the inverse problem. And just to finish, let me maybe suggest some perspectives towards the future. Okay, perspectives. So I think it would be nice to have a better understanding of the geometries of the examples of Zoll metrics. I don't know, compute the diameter, the volume, how these things are related, the possible curvature, maybe the spectrum. I don't know. There are several geometric questions that seems nice to be asked for those manifolds. And also, maybe we should try to understand the moduli space. Right? Okay, so for this problem, the moduli space is solved, but for the general problem, right, so it would be nice to compute the homotopy groups, right? But it's open even in dimension 2, whether the space of Zoll metrics is connected or not. Okay? So it would be very nice to have a proof that this space is connected. Now, the other natural question that you might ask is about codimension, higher codimension, right? So instead of looking at minimal hypersurfaces, maybe you want to look at something of higher codimension. Other thing that I think is reasonable is to study analogous problems, analogs in calibrated geometries. So in these geometries, there are distinguished sets of planes, right? So, and you know that if a surface is tangent to such special planes everywhere, then this surface is minimal. So it seems reasonable to pose the question in this setup. And then, just to close the circle of the talk, let me state here the relation to isosystolic inequalities. So, roughly speaking, a systole of a sphere, say, could be defined. So this is not a standard definition, but it's okay for the talk. So you take the infimum of the area of sigma, where sigma is some minimal hypersurface. Let's take a minimal Sn minus 1, okay? So an interesting question about this invariant is the following. So are there subsets X of the space of all Riemannian metrics in the sphere, metrics that have a fixed volume, say 1. So is it possible to show that for metrics in this set with volume 1, you have an upper bound for the systole by a constant that depends only on the set? Okay, so this is a typical example of isosystolic inequality. And as I told you, I suspect that the maximizing metrics, so the metrics that realize the sharp inequality, are Zoll-like. Okay, so at the beginning, this seemed a good conjecture. So in dimension 2, it's fine by the work of Umberto Hriniewski and his collaborators. But in high dimension, I mean, I didn't know nothing. So nowadays, I mean, the initial conjecture was that all Zoll metrics are maximizing metrics. But because of my work with André and Fernando, I know this is false. Okay, so I know examples of Zoll metrics which are not maximizing, say, inside a conformal class of metrics. However, I still think, because the maximizing condition implies that there should be many systoles around, kind of equally distributed, I think that these Zoll metrics are good candidates to be maximizing metrics. So if we understand better the geometry, maybe we can understand better this problem. Okay, so thank you very much. Can you see?
There are questions?
Is the notion of Zoll-like, can you generalize that to other manifolds other than Sn?
Yes, you can. So I will say a bit, okay, so I asked my PhD student, my first PhD student, Luciano Luzzi, who is in the audience, to work on the analogous problem on CPN. Because CPN is an example of calibrated geometry. The CPK is inside CPN with the standard metric, are totally geodesic. So, and they are, for every given complex K-plane, you find a unique CPK going through that point with that given tangent plane. So, I mean, there are several analogous questions that that appeared in this talk that Luciano is looking at. He knows how to answer some of them, so maybe you can ask him.
What about RPN? Is it a lot easier? I
RPN,
mean,
that's an interesting point. So because of this correspondence, because of this equivariance, you can actually check that all those metrics here are invariant by the antipodal map. So they all descend to RPN. So you can find non-trivial examples in RPN. And this is interesting, right? Because in 2 dimensions, I don't know if you know this theorem of Green that tells that an RPN, so a metric on S2 that is Zoll in the classical sense, and which is invariant by the antipodal map, must have constant curvature. Right? So in 2 dimensions, only trivial examples. Here, you see many examples. Okay? Even non-homogeneous examples. However, here I'm imposing an ansatz, right? So I'm imposing the condition that the Zoll family is the family of equators. In the general context, I don't know. I conjecture, so yeah, there are some indications that maybe in the conformal class of the canonical metric of RPN, maybe the constant curvature metrics are the only ones that are Zoll in this sense. Yeah, this is my conjecture.
I think it's a similar question. Can you relax the condition on the definition of Zoll family to avoid this uniqueness of planes, and or you just have somehow a covering family?
Yeah.
So would you get something different for metrics, close to the canonical one?
If you don't impose, maybe you just want to know that through each point passes a. This seems a bit. Yeah, this. Yeah, this I don't know.
Because in dimension 1, the motivating example that you gave, you impose no condition at all, right? You just ask every geodesics closed.
Yes, but geodesics have this property, right? So given any point and direction, there goes a geodesic. So this condition was natural even from this perspective too. But if you remove this hypothesis, I don't know what you can do. My feeling is that the condition A is the condition that's maybe unnecessary. Maybe a posteriori you can prove that the parameterizing space is RPN.
And another question that how regular are your solutions? And of course, I'm interested to know if you have algebraic or many algebraic examples of this.
So those ones here are analytic. You can pass from here to here, and you see the bijection here is explicit, so you can check. It's analytic. It produces analytic metrics. In the deformation theorem, we produce smooth metrics, not necessarily analytic. And yeah, it would be interesting to find an algebraic example. Actually, let me mention that even though we have this classification, even though we have the deformation theorem, we cannot use it directly to say produce an example of a sphere of revolution in Rn+1, like the original Zoll example. Because this is a very abstract theorem, we don't have control if the matrix can be isometrically embedded in Rn+1, right? So, yeah, maybe, and this is why I proposed the first question, right? So, maybe we should look for spheres of revolution in some Rn that are Zoll in this sense, and maybe they are algebraic, or there is something interesting in this direction to be said.
Any other question? So let's thank Lucas again.